Okay, so welcome to lecture 3 of boundary value problems and index theory. So let me start today a bit slowly with some errata that I want to address. So the first thing I want to address, so some errata so far. So the first thing I want to really point out is there's a missing condition, or the notion of a manifold with boundary is actually not formulated correctly in my actual lectures when I gave it the first lecture. So the condition that's missing is that we need to say that for all P in M, there exists some UP. And remember, we have this map that takes us from UP into Rn. We said that this was an injection, but it needs to be a lot more. Sorry, Rn plus. So this cannot just only be an injection. This really needs to be a homeomorphism. To its image, and its image psi of P is open in Rn plus. Okay, so in the subspace topology of Rn plus. So this has been corrected in the lecture notes. And the other thing that I really want to say is that equivalently, we can formulate it by saying either it's open in Rn plus or it's open in Rn. And that can be useful typically in calculations. But all of this is now included in the lecture notes. So the other point is that when we talk about a point on the interior, we really need to say that there exists some chart in the maximal atlas. Such that P is in U and U of a psi of U is open in Rn. Sorry, psi of. So it's enough to say this by the comment that I made just before. The other errata that I have is to do with the previous lecture in the last lecture. So the first thing is I said that LP is separable, but LP, we have to exclude P equals infinity. Okay, so I forgot that I actually talked about P equals infinity at the time. So this is separable for P between 1 inclusive and infinity exclusive, right? So L infinity of ME is not separable. The one other thing that I wanted to point you to was a bit of a clarification. So it was really wrong of me to recall that we defined this norm, and actually someone asked me a question about this norm. So this is in B1, this is in B2. So when we have an unbounded operator, we have this norm. And I was asked whether this is the graph norm. That's exactly right. This is exactly the graph norm, and that's the terminology that we should use for it. I actually said operator norm last time, and that was not correct. So what I was actually trying to say is the short form, that this is the norm related to the operator. That statement is true, but the notion of an operator norm has a meaning in operator theory, right? So the operator norm for a bounded operator, so the operator norm is simply the sup of x in, say, B, such so say norm x equals to 1, right? So this is the operator norm when we have a bounded operator from B into, say, B prime, right? So this is B prime. So this is the operator norm. This is what's typically considered the operator norm. So this already has a meaning, but what I was really trying to say there is this is the norm associated to the operator T. Okay, so with that in mind, let's move on. So today I want to talk about a topic, so hopefully we're going to move on to some geometric things also today, but the first thing I want to start today is with the topic of projectors and decompositions. So as this course moves along, you'll start to see that the ability to decompose a Banach space or a Hilbert space is really paramount to the consideration in the context of boundary value problems. So we really need to talk about how to decompose spaces. So let's fix some terminology here. So let B be a Banach space. So the reason I'm still, so all of what we will do in this course will be on Hilbert spaces. But the reason I'm really talking about Banach spaces here is that despite the fact that we're working with Hilbert spaces, when we talk about things like decompositions, it would be it's closer in philosophy to what happens in a Banach space than a Hilbert space, because we cannot really use notions of orthogonality that are in a Hilbert space because of the way of what comes out of the boundary value problems themselves. So let's make some definitions. So okay, so so for B1, B2, which are subspaces of B, and I'm assuming that they are not necessarily closed. Maybe I should change this to 2.5. Okay. We write B equals B1 plus, well, not B equals, but we write B1 plus B2 to denote the vector space U plus V. Oh, let me just define it actually. What am I doing? B1 plus B2 is defined as U plus V such that U is in B1 and V is in B2. Okay, this is just the vector space B1 plus B2. Okay, so if B1 intersect B2 is 0, then we write B1 plus B2. Okay, so the little a here, the a corresponds just to saying this is the algebraic sum. Okay. So lastly, okay, so now I'm going to assume that B1 and B2 are closed, and I'm going to write so we can say that B is equal to this decomposition B1 plus B2. Yeah, if they're closed, then we write this. Okay, without the little a. And the reason for this will become clear. So then in this case, we say that, oh, okay, sorry, I'm missing something here. So I want to say here that, so we say here that B1, B2 are algebraically complementary. Okay, so that's the condition that the intersection is empty. Or not empty, but it's zero. It's a zero vector space. So in this case, we say that B1 and B2 are complementary. Okay, so the reason I'm really writing B equals B1 plus B2 here is because I want the sum, this sum to be a closed subspace, right? So equivalently, I could have just said that B1 plus B2 is closed, but we have a Banach space B here to begin with, right? So we really want to talk about decomposing this Banach space, so I'll write it in this way. Okay, so we say that these are complementary, and another piece of, another bit of notation I want to really fix here is that if I have, if B1 is a subspace of B and there exists B2 in B such that, so closed, so I should say closed. And there exists B2 in B closed such that B1 intersect B2, so such that B1, B2 are, well, okay, sorry, I'll just write B equals B1 plus B2, then we say that B1 is complemented. So I'm just fixing this notation here so that if you're reading these things in the literature, you know what these words mean, okay? All right. So let's have a look at some examples. And for this examples, I'm going to stick more or less exclusively to Hilbert spaces, except for a few examples, because that really highlights that things can really go wrong even in Hilbert spaces, okay? So H is a Hilbert space. And H1 is a subspace. Then we have the orthogonal complement, right? So this is the U in H such that UV equals 0 for all V in H1 is a closed subspace. And we have that H equals H1 closure plus H1 perp. Okay, so in a Hilbert space, given any subspace, there is always, its closure always has a complementary subspace. So first of all, it has an algebraic complement, so the H1 perp is an algebraic complement of H1, and the sum is now, well, and the closure of this subspace H1 is now complemented by the orthogonal complement. Okay, that's the first thing I want to say. The next thing is a non-example. So if we have H1, H2 complementary, i.e. they're closed, and so I should say that these are closed subspaces, and H1, closed subspaces such that H1 intersect H2 is 0. okay? Because my notion of complementary, I have to, the notion of a complement really requires the sum of the vector spaces to be closed, but I'm not going to assume that here. So suppose we take algebraically complemented subspaces that are closed. That's what I'm assuming, right? I.e. H1, H2 algebraically complemented and Hi closed, just to emphasize. This does not imply that H1 plus H2 is closed. Okay, so the sum of closed subspaces is not necessarily closed. So let me give you an example. So this is due to Robert Israel. This is where I know it from. An example he gave. So okay. So the vector space that the Hilbert space we're considering is little L2, and I'm going to consider the sequence H1 to be the sequences Hn, n in Z, such that H2n is 0, okay, for n in n. And H2, I'm going to consider the sequences Hn, again, oops, n in n here, not Z. N in n such that H2n plus 1 is equal to n times H2n, such that n is in n. Okay, so these are algebraically complemented subspaces, right? So if X is in H1, well, maybe say H, little h is in H1 intersect H2. So this can only happen if H2n equals 0, and then we also have that H2n plus 1 is equal to n times H2n, so this is again 0, right? So that means that, well, H equals 0. So it's certainly algebraically complementary. Okay, so why is H1 closed? So suppose we take a sequence xi in H1 such that xi converges to x. So I can write my sequence xi as equal to hni, and this is going to converge to x equals, say, hn. So the convergence is precisely that the sum of hni minus hn squared. So what's this equal to? This is precisely equal to the sum j of, so in this sequence, only the 2n is there, right? So h2j squared, so h2n is 0, so this sum is exactly going to be equal to the following. So h2j plus 1 I minus h2j plus 1. Okay, so these are the two sequences. So this thing now tends to 0. So that means that h2j is equal to 0. Okay, because this tends to 0. And that precisely means that h is in h1, x is in h1, right? So this is a closed subspace. So similarly, h2 is closed. Okay, so yeah. So H2 is closed. So if we take xi in H2 with xi converging to x, then what we have again when we split off like this, so we get sum n h n I minus h n squared is equal to j h 2j I minus h 2j squared. Oops, there's a square missing here, sorry. Plus some nh2j I minus h2j, oops, 2j plus 2j I minus h2j plus 1 squared. So again, from this we can deduce, so what can we deduce? That this is, that h2j plus 1 is equal to nh2j, and that means that x is in H2. Okay? All right. So, okay. So now we show that H1 plus H2 is not equal to H. So let X be just an element in H, such that, so let's take X equals Hn, and I want Hn to be equal to 1 on n plus 1. Okay, so obviously this is a sequence in L2, right? So this is clearly a sequence in L2. Now, suppose there exists a U and a V in H1 plus A H2 such that X is equal to U plus V. Okay? So, the sequences in H1 have, so U is in H1, sorry, I should say U in H1, U in H1, V in H2. Okay. So the sequences in H1 have the component 2n being 0. So so U2n is equal to 0, and that implies that V2n has to take the value, right? So it has to take some value. So and we know what the V2n has to be. So V2n is 1 on 2n plus 1, and that implies that V2n plus 1 is equal to n over 2n plus 1. Okay, so this determines what the vector V has to be, because the elements of U don't have a they're 0 for the 2nth entry. So now if we take the Vn squared, so this is going to be equal to the sum of n squared on 2n plus 1 squared, but this is equal to infinity, right? So we cannot have such a decomposition. So this illustrates, so it's really important to get the point across that when we're dealing with the canonical sort of subspaces in the complements that we have, which are the orthogonal complements in Hilbert spaces, everything goes okay. But there can be subspaces, or there can be algebraically complemented subspaces that are closed, which do not sum up to the total space. Okay, so this is an important point. So of course the thing is that yeah, so anyway, okay. So this example also goes across to any separable Hilbert space, because if we have a separable Hilbert space, works for any separable Hilbert space, since H separable means that there exists an isomorphism from H to L2, right? Namely, take a countable dense subset and map it to the usual bases. So this is an iso. So that's the first thing I want to say. So the second thing I want to say is we can have, again, a Hilbert space being, yes? Algebraically closed means that, algebraically closed, you mean algebraically complemented? So the question is, what is algebraically complemented? So algebraically complemented means that these are subspaces such that H1 intersect H2 is 0. Okay, so that's true. Okay. So the point that was made was this example does not show that this is not closed. It just shows that it's not the whole space. You're absolutely right, and in fact, it's because I forgot something. So to show that it's closed, it's not closed. So H1 plus a H2 not closed. So for that we show that H1 plus H2 is dense. Okay, yes. Thank you for that. That's a very good point. So let's consider LF to be the sequences xj such that xj is 0 after finite j. This is certainly a dense subspace of L2. LF is in L2 and it's dense. Now the point is that LF, it's easy to check, is also in H1A plus H2. So that must mean that H1 plus H2 is dense. So we have a dense subspace that's not the whole space, and so therefore it cannot be closed. Thanks for that. That's a really good point. Okay, the second thing I want to, so let's just move on to the next example. The second thing I want to say is that we can actually have the Hilbert space H summing up to the algebraic sum of two subspaces where H2 is closed and in fact finite dimensional. So it's as good as it gets. But H1 is not closed. Okay, so that's the other strange thing that can happen in this world. So how do we prove this? So again, let H equal little L2 and let F be an unbounded functional. Well, let's say R because we're working on R. So I won't talk about the existence of such a linear functional. It does exist, right? I don't want to. It's we're straying too far away from things if I try and also get into that. So now we fix some x naught in L2 such that f of x naught is equal to 1. Okay, so of course for some element we can find this. Okay, now for x in L2 we have x minus phi x x naught, so x is equal to this plus phi x x naught. Okay, so clearly, so this is in the kernel, and this, well, this is a one-dimensional, so this is in the one-dimensional space R x naught. Okay, so so it remains to show that so if we have some functional phi from a Banach space into C or R, so I'll say R here, unbounded. Sorry, yes, thanks for that. So this is a more abstract fact. So if we have an unbounded functional, that means that the kernel of this phi is not closed. Okay. So how do we prove this? So unbounded means that we can find some sequence in the Banach space such that phi of xn exceeds xn n xn. So there exists some sequence. Okay. So define now y of n is equal to x minus xn on phi xn. Okay, so clearly we have that yn now converges to x. Okay, so I should say, so we define, okay, so we define this, so x is chosen such that phi of x is equal to 1. Okay. So now if we take f of yn, this is equal to f of x minus f of, phi of yn is going to be phi of x minus phi of xn divided by phi of xn, and this is equal to 1 minus 1, so this is 0. So that means that the yn is in the kernel. So if yn is in the kernel and we have that the kernel is closed, it would imply that x is in the kernel. But this contradicts that phi of x is equal to 1. Okay, so this highlights where things can go wrong and what can happen in Banach spaces. Just two quick remarks before we move on, because we want to get to some theorems. So there are subspaces when we go into Banach spaces. So if we consider, so remember C0 are the sequences xn such that the limit n to infinity of xn is 0. So this is a closed subspace of L infinity, but it is not complemented. And in fact, this is really a characterization of a proper Banach space. So a theorem of, this is just a passing comment, so this is a theorem of Linden, Strauss, and Freire from 1971 that if a Banach space is isomorphic to a Hilbert space, if every closed subspace is complemented. Okay, so there's a lot of rich structure theory with all of this stuff. We don't need to get into these last two aspects because we stick to Hilbert spaces, but I just really want to emphasize that things can still go wrong in the Hilbert space setting. Okay, we can have lots of weird things happening, so we have to be careful. I think I've spent a bit too much time on this than I wanted to, so let's move on. So connected with, yes, question? Sorry, you broke up, I couldn't hear. No, complemented means there exists. So if we have B1, which is in B, is complemented, so this is closed, right? If there exists B2 closed, such that B is equal to B1 plus B2. That's what it means for it to be complemented. The intersection has to be empty, right? Sorry, not empty, but 0. Otherwise, we write a plus. Yeah. Okay, so let's now move on. So connected with all of this, it's of course an if and only if, because so the question is it an if and only if in the theorem of Lindenstrauss and Zafiri? Of course, it's an if and only if because every Hilbert space is a Banach space, and in a Hilbert space, every closed subspace is complemented by the orthogonal complement. Okay. So the question there really is, how do you characterize the Banach spaces which are Hilbert spaces or isomorphic to Hilbert spaces? Okay, so anyway, so all of this leads us to projections. So we say that a bounded map from a Banach space into itself is an idempotent so it's an idempotent, which means that its square is equal to itself, is called a projection or a projector. Okay, so we'll see this. We'll see why in a second, and we say that P projects to PB along 1 minus PB. I have to admit I've given this in the wrong order probably, so maybe this proposition should precede it. Okay, so PB and 1 minus PB are complementary subspaces. Well, actually, let me not write. Are closed complementary, and at the risk of stressing the point, I should write B is equal to PB plus 1 minus PB. Okay, so we already have by hypothesis that P is bounded. So let's take some xn in PB and suppose that xn converges to some x. So boundedness means that, so idempotency means that p squared xn, so which is equal to p of xn, now converges to p of x. Right? So, moreover, we have that xn is in p of b. So if xn is, so okay, maybe I should have written this slightly differently. Okay, so let me erase this for a second. So xn, we assume xn converges to x. So we know that there exists some xn tilde such that xn equals p of xn tilde. So what can we deduce from this? We can deduce from this that p of xn is equal to p squared of xn tilde, which is equal to p of xn tilde by idempotency, which is again equal to just xn. So then I can write xn is equal to p of xn. This is what I wanted to write. And we know that the xn converges. So it means that this thing now we know converges to p of x, but this must be equal to x because xn also converges to x. Okay? So what does this show us? This shows us that x is equal to the p of something, which is again x itself, and this is in p of b. Okay, so that's the first part. The second part, so we claim that this is complementary, so x is in p of b intersect 1 minus p of b. So let's suppose that. So that means that x is equal to pb, and it's also now, because it's in the range of, so okay, maybe actually I should also say 1 minus p is also an idempotent, so 1 minus p b is closed, right? I should just make that remark. So here I can now write this, because I assume that x is in both p of b and 1 minus p of b, I can just hit this with 1 minus p of b. And so that means I get from this that this is p minus p squared b, but it's an idempotent, so this is 0. Okay, so now if we have just some element b in b, we can write b as equal to p of b plus 1 minus p of b. And this is the decomposition, right? So this is exactly that b, we have this being in pb plus 1 minus pb. Okay. So this shows us that projectors give complementary subspaces, but it goes the other way too. So suppose that b is equal to some b1 plus b2. Then there exists a projection p to b1 along b2. Okay, so for a projection you always have to have not just the image but also the kernel. So the kernel is what you're projecting along. In the interest of time and other things, I won't get into it. So this is an exercise, and it's, let me just give a hint maybe. Closed graph theorem. Right, so just a remark when we really deal with projectors. So it's really not enough that we have projectors, say, going from B into maybe some B prime, which is a subspace of B, where the topology on this might be different, right? We really need it to be bounded in order for everything to work. Otherwise, things fall apart, okay? So it could often be that we have some dense subspace of a Banach space that we're mapping into, but that doesn't necessarily mean that the projector restricts. So it will be an idempotent, but it might not be a projection that restricts in terms of bounded operators to that subspace, right? So is vital. Okay, so that's just a side remark that I'll make. Okay, so now let's couple this with the things that we talked about in terms of reflexivity and annihilators, right? So let B1, B2 be... It's vital for being able to decompose the space. If you don't have boundedness, you cannot just do it with idempotency, right? So here in the proof, so the question was, I keep forgetting to ask to repeat the question. So why is the boundedness vital? So here in the proof, we really use the fact that when X converges, P of X converges. It's vital for the projector, for P being able to decompose the space into closed subspaces. Precisely. So here we can see where the boundedness is used, not just the idempotency, right? So idempotency and boundedness, they both are vital. I mean, you could possibly think of an idempotent map. So P maps into some subspace, but maybe it's not bounded in the topology of. So this is a subspace, but it's some subspace which is of a different topology, right? Maybe it's a stronger topology, and then you still have that this subspace is sitting in B, but it's changing spaces. And because it's a subspace of B, P can be an idempotent, but it might not be bounded as a map from B to B. Okay, so that's just a side remark. Okay, so let me now move on to looking at coupling these projectors with these perfect pairing. So this is a perfect pairing. So this notation throughout I will denote by perfect pairing, and I will say reflexive to mean that either B1 or B2 is reflexive. Just shorthand. Because we saw already that if one is reflexive, the other is reflexive. Okay. So now the proposition. So let P be in B2 projector. So the claim now is that the induced adjoint map, the induced adjoint map is a projector. Okay, so let me quickly prove this. This is not so hard to prove. So let's consider let P star C in B1 star, sorry, B2, the adjoint space, be the canonical adjoint. So the fact that I'll use is this exists with the domain of P star of C being equal to the whole of B2 star, right? So this does not require that reflexivity, actually. So where reflexivity again is used is, remember that the domain of this width. So so remember that the projector is always a closed map. So this in particular says that the closed graph theorem tells us that this adjoint projector, the canonical adjoint, is bounded. Now we're just pulling back, so the domain of the P star, and this is what requires reflexivity, of course, because we need to know that this phi 2, which is the map, so what's the map? So this is maybe phi 1. So phi 1, B1 equals B2, right? So this is what we need, sorry, B2 star. So this we need to know is the full space, and that's where we use reflexivity. So this is now the domain of P star of C, and by the definition of the map and the closed graph theorem, we have that P star is a bounded map now on B1. Okay? So now let's look at what happens when we act on this. So this is going to be P star V P of U, and then we take V P squared of U, but this is now equal to P of U, and we pull this back, V of U. So because this is a dual pairing, again, remember I can recover the norm of this by taking the sup over the U, for which the norm is 1, and that allows me to conclude that P star squared is equal to P star. Okay? So that proves that it's a projector. So the point is that when we have a decomposition of one space, namely the space B2, and we have projectors, then there are induced adjoint projectors with respect to the duality, with respect to the perfect pairing, which decomposes the space B, the other space that the space B2 is in duality with. Okay. And I'll just end with this. So if we have B1, B2 reflexive, and P B2 projection, then P star B1 P B2 is reflexive. Okay, so all right, so the proof of this I'll leave as an exercise, except I'll make the following note. Any closed subspace of a reflexive space is reflexive. And then the rest is an exercise. Let me just also draw a picture just to sort of illustrate what's really going on. So we have this being PB, so this is PB2 plus 1 minus PB2. And then we have B2 in duality with B1, so B1 is going to decompose as B1 plus 1 minus P star B2. Oh, sorry, B1. So the claim is that these spaces, and of course, well, maybe I won't draw a dotted. Of course, we can say the same thing about 1 minus p, right? The situation is symmetric. So these are the spaces that are in duality. This is not a part of, sorry, the question was, is this a part of the proof? No, this is not a part of the proof. This is just a diagram of what's going on, right? So we have a decomposition of B2 by P, and then we have a decomposition of B1 by P, and the spaces that are in duality are the spaces in the box. Okay. So now in the remaining 30 minutes, let me move on to some concrete things. Okay, so more or less the abstract things for the moment are over, and we're going to get back to something more concrete. So what I want to talk about, so we've seen so far that densely defined operators are really the heart of what we're going to look at, because we need dense definedness to look at, we have to look at unbounded operators. We're forced to do that, as we'll see. And when we deal with unbounded operators, we also don't want to deal with adjoints. And to deal with adjoints, we really require dense definedness. So for the class of operators that we want to apply all of this abstract machinery to, we have to really hunt out some good dense subsets. So I want to just make a remark or show the density of compactly supported smooth sections in the LP space of a manifold with boundary. Okay? So that's what I want to talk about. So I'm going to start with a lemma about ordinary manifolds. Okay, so the lemma is let M prime be a manifold in the usual sense. So no boundary, and fix mu a density M prime. Maybe we should call it M tilde, I don't know. I'll leave it M prime. So we fix a positive density and a metric H, metric on E. So I could have said all of this more succinctly, but anyway, I could have just said that M mu is a, yeah, let me change this. Sorry, let me say it more succinctly. So let me just say that M prime mu is a measure manifold. Okay, in the usual sense, I'll keep that as before. M prime is empty, and M prime mu is a measure manifold. Okay, so that means that mu is a positive density. We should use the terminology that we've defined. So we have E being a vector bundle over M prime, and H a metric on E. Okay. Then C infinity C of M prime in E is dense in LP M prime of E for P in the range 1 to infinity. I'll try and get used to this notation in the book. Okay. So this is what I want to say. So how do we prove this? So first, we note that on a manifold there exists, in the maximal atlas, we can find charts uj psi j such that Vj is contained in the closure of Vj is contained, so Vj open and, sorry, Vj closure is contained in here and Vj is open, such that M prime is equal to the union of these Vj's, right? Okay, I should say open Vj compact. Okay, so I really want the Vj's to be compact. So if we fix such a cover, so maybe call this script C. So then we have maybe script P. Okay, sorry. Script P. This is a partition, a smooth partition of unity subordinate to the cover C. Okay, so the first thing is, let me define LP subscript C of M prime in E. So these are the U in LP M prime of E, such that the support of U is compact. So so I should say let then LP compactly supported M prime in E is dense in LP M prime of E for P in the range that we talk about, right? Certainly not for infinity. The proof of this I will leave as an exercise. Okay, so it's an application of the dominated convergence theorem. Okay, so I'll leave that. The more interesting thing is the following. Let U be in LP C M prime of E. Then there exists a UN sequence that's smooth, M prime, sorry, such that UN converges to U in the LP norm. Again, I want to emphasize that P is in this range 1 excluding infinity. So how do we prove this? So let's fix such a U. So then there exists some number n such that U is equal to, now the sum equals I equals 1 to capital N of e to I u. Okay, so this is from my partition of unity. Okay, so now let me take rho be a mollifier. Well, let's take it to be the standard symmetric mollifier. The question was, is the open cover countable? Yes, it's absolutely needs to be countable. So on a manifold, we can always find an open countable cover because it's a second countable space. Okay, so let's take the standard symmetric mollifier on Rn. So what is that? So i.e. Rho of x is equal to some normalizing constant e to the minus 1 on 1 minus mod x squared. So this is the Rn for x less than or equal to 1 and 0 for mod x greater than or equal to 0. So Cn is a normalizing constant so that the integral with respect to the Lebesgue measure is equal to 1. Okay. Now, consider ui equals eta I of u, which has support in this vi. Okay, so inside this I we can choose, so we can choose now, so maybe I should say yeah, okay, so maybe I should actually, before I say this, I should say here fix some epsilon to be chosen later. Okay, so the actual choice of the epsilon will come later. So given such an epsilon, inside each for each of these ui, we can choose delta I, which depends on epsilon, such that, so if I take eta I u, okay, sorry, I'm writing ui here, ui composed with psi I inverse minus ui composed with psi I inverse. So now this is really a map from psi I of u into E. So I should really have, yeah, so I should really have said that, sorry, this is an oversight. I have to really match up the open sets that I considered originally with trivializations of E. Okay, so okay, so that's a bit of a nasty place to try and put this now. So okay. Okay, so maybe I'll just move this. Can you repeat that question again, please? The functions for the partition of, so the question is, don't we have a partition of unity? So this is an eta I. The eta I is the partition of unity. So let me just say that, recall that the ui psi I, so this is a chart, and we assume this in this chart E is trivial. We can always match this up, right? We can always find a cover to make that happen. And then the vi is contained in the ui. The vi closure is also contained in the ui, right? This is open, and that's what we're assuming. Okay, and so I should have really said, to begin with, we always choose these charts so that everything matches up with trivializations, local trivializations of E. I have to apologize. My handwriting is shocking. So the confusion seemed to be caused by the eta I and the ui looking very similar. Sorry about that. Okay, so anyway, let me now continue on with this. So I'm going to look at the difference between the ui composed with the psi I minus, now I'm going to multiply this again by psi I composed with sorry, I meant I composed the eta I with the psi I inverse, and now I mollify. And what do I mollify? I mollify the ui composed with psi I inverse. Okay, so this is a map. So this is a map from psi I of ui into, and I can compose it with the trivialization. So I can consider this a map into C some capital K, which is the rank of the bundle. Okay, so that's how I'm really considering this, and I'm just mollifying, right? So in each entry, I just mollify. The number. So the number on the row is this delta I of epsilon. Okay, so when we set up the mollifiers, we have an exponent, right? Because the mollification so the question is, what is the exponent on the row? Okay, so I should have maybe explained the mollifiers a bit more. So let me just write this and then I'll explain the row. So this in the LP norm in psi I of ui into E, we can make this less than epsilon on 2 to the n. Okay, so the capital N here was from the sum of these charts that we had, and we can always organize this. So what is the row I? So the row acting on the delta of x is delta to the minus n row of delta x. Okay, so when we mollify, we want to do this because we want this to be an approximation of the identity. And then the integral of, so the mollification of delta of some f is vector valued is just simply in some frame we write integral rho delta of x f alpha x. I'll just move this to the next line. At x is equal to the integral rho delta x f alpha x minus y e alpha, where e alpha is a frame, right? So this is with respect to the Lebesgue measure. Maybe I should write d Lebesgue. Okay, so without getting too distracted by all of these things, I just want to really point out the way in which why this estimate works. I mean, the point here is that the density mu is smooth. So inside the VI, there exists some constant, say Ci, such that mu can be bounded against, say, dx1 up to dxn, which is the natural form inside this inside this chart. We can bound the density mu x. So there's Ci greater than or equal to 1, such that this bound holds. well, actually, let me get rid of this because I'm writing not, you know, Ci inverse is, so this inside Vi is bounded by some constant. So all these constants can be absorbed in this mollification, right? Because we're really looking at the difference between two things. And when we're looking at the difference between two things, we know that inside this localization, things converge to zero. So given some epsilon, I'm going to choose a delta I, so I'm going to fall within epsilon divided by 2n. Okay, so that's what we're doing. Okay, so all of these constants can be absorbed into the delta I, right? So that's why I'm making a choice of delta I. So now, so I said before that for epsilon to be chosen later. So now I'm going to choose epsilon equal to 1 on n, and I'm going to define un to be what? This is going to be the sum from 1 to n. So okay, so I should maybe also say that yeah, okay, it doesn't matter. That's good enough. This is going to be eta I, and I'm going to now write exactly this expression. So, but pulled back onto the manifold. So I'm going to write rho delta I 1 on rho delta I 1 on n star eta I composed with psi I, sorry, ui composed with psi I inverse composed with psi I. Okay? So this is what I'm going to write as un. And it's easy to see that this is now a compactly supported section in M prime into E. And now this estimate that I wrote up here, so combining this estimate, we have that U minus UN is going to be the sum I equals 1 to n of the localizations, right? So this is going to be ui minus the eta I of un that we've written. So I apologize again. I'm going to put u superscript n here to avoid the confusion, right? So my sequence is superscript. And so now we ensure that this is going to be less than 1 on n, 1 on 2 to the n. And so obviously this is less than 1 on n. Okay, so this is my sequence as promised. So lastly, it should be easy to go now from this to saying that this space is dense in LP of M prime E, and this is just an epsilon on 2 argument. Okay, so we first find something to approximate an LP section in compactly supported LP functions, and then we, from the previous step, we can smooth this. So maybe I'll also just say this is an exercise. It's just good to try a hand at that. Okay, so that finishes the lemma. So how do we now get to manifolds with boundary? Okay, so proposition, let M be a manifold, well, I'll say mu measured manifold with boundary. then C infinity CC of ME, well, and of course we have a vector bundle and a metric on the vector bundle and so on and so forth. Okay, so I won't really spell that out. Then C infinity CC is dense in LPM of E. Okay, so what is the proof of this? So remember that M, the interior of M is a manifold without boundary. Okay, so clearly M prime, which we set to be the interior, is a manifold without boundary, as we've mentioned. And also the mu restricted to M prime is a density, positive density. So everything restricts. So let me define U to be U restricted to M prime. And clearly this is U restricted to M prime or M open. So this is clearly an LP section now in the interior. Okay? So by the lemma, there exists UN, which are compactly supported functions on the interior, or on the interior, such that UN converges to U open in LP. So I really should have said that. Again, we really should emphasize here that this is for P in 1 to infinity exclusive. Okay. In LP of M E. Now, define UN as follows. So this is going to be UN of X when X is in M open, and 0 when X is in the boundary. Clearly, this is now, what's the picture? So if this is the boundary, the support of, say, this UN for some UN, so the support of it doesn't touch the boundary anyway. So if I extend by 0, I still get something smooth, right? So clearly, UN is in C infinity CC of ME. Now the claim is that this is the desired approximation. Okay, so why is this the desired approximation? I take UN minus U, I raise it to a power of P, LP, and now I get an integral UN minus U to the power of P, H d mu of M. But now I'm going to split up. So I have two measurable disjoint subsets, so I'm going to split this up into M open, UN minus U, H, it's a U, P d mu, plus the boundary term UN minus U P H d mu. But the boundary is a set of measure 0. So this is equal to 0. And so we're just left with UN interior minus U LPP. But this goes to 0 by design. So that finishes the proof. Okay, so it almost feels like cheating, and in some sense it is, but the point here is that at the level of LP spaces, we're really dealing with integrable spaces. And when we're dealing with integrable spaces, you don't really see things like boundary. Okay, so boundary regularity didn't really come into play here either, right? I could have just replicated this in any setup where maybe the boundary is just a set of measure 0. So the interior is really the thing that governs what happens at the level of this LP scale. Okay, so we'll see from the next lecture onwards, when we start talking about differential operators, that's really when we are going to start to see the boundary. Okay, so I'm going to finish a few minutes earlier, so maybe I'll just open the floor for questions if anyone has questions. Mm-hmm. The question is this theorem of Linden, Strauss, and Tazrifi, sorry, I get the name wrong. The theorem of, where is it? Linden, Strauss, and Zafriri, is this an isomorphism? To be honest, I'm not sure. I haven't really looked into the Banach space theory. I just gave that theorem as something to show that spaces that are complemented, where every closed subspace is complemented, is very close to a Banach space. So I don't know, and I can't say that this is really saying that norm actually polarizes. But just on that point, let me just say that this also shows, I mean, maybe it's a more sophisticated argument, but this also shows why a space like LP cannot be a Banach space, cannot be a Hilbert space, right? When P is not equal to 2. Are there any other questions? So I apologize again for my handwriting. Please do call me out on it. It is a disability that I cannot seem to shake off. So believe it or not, I sometimes find it difficult to read my own handwriting, which is why I typically type up anything that I do that is of any importance. But okay, if there are no more questions, I'll end the lecture there and see you on Wednesday.